Okay, we were talking about the directional derivative in the last video, and the gradient vector came up. And there's some really important properties of the gradient vector that you're going to want to know about. Okay, going back to our directional derivative formula, we want to find the slope of our graph in any direction u. It's the gradient vector dotted with u, right? That's our, and by the definition of the dot product, the directional derivative can be thought of as the magnitude of the gradient times the magnitude of u times the cosine of the angle between them. Okay, so suppose we're interested in the maximum directional derivative, the biggest possible slope based on where we are on some surface, right? Remember these, think about a three-dimensional surface like our mountain on the last example. You're on the surface of a mountain and you're looking for what is your steepest slope. Well, if we think about what would make this maximum, okay, remember that, okay, the magnitude of a unit vector is always equal to 1, right? That can't change. By definition, that's 1. The magnitude of the gradient is going to be whatever it's going to be. What's the maximum value for cosine? Well, the cosine of theta maximum value is going to happen when it's 1. And that's going to happen when theta is 0, okay? This tells us two really important things, okay? Number one, the maximum directional derivative then is going to happen when, okay, again, the unit vector's magnitude is 1 and when the cosine is 1. And if that's 1 and this is 1, then what is our maximum derivative going to be? It's, what are we left with? Just the magnitude of the gradient. So the magnitude of that vector will be your biggest possible slope, your biggest rate of change, okay, of your function. And then the other thing is that happens when theta is 0, which, what does that mean? That means the direction you're computing your slope in would be, if these two are, if theta is 0, it means your gradient vector is pointing in the direction that you want to move in for that maximal change. So the maximal directional derivative is going to occur in the direction of your gradient when theta is 0. So your gradient vector tells you a lot of things. It tells you what direction you should be facing to get the maximum rate of change of your function, and then the magnitude of that gradient will tell you the actual maximum directional derivative. Okay, let's see this in an example. So I've got a function 3xy minus x squared at -1, 1. There is a z value, right? I could plug in x and y to get a z value. And I want to know what direction is the maximal rate of change and what is that maximal rate of change. So as we saw, it's related to the gradient. I would do f sub x, f sub y, 3y minus 2x, and then 3x for f sub y. Evaluated at my point gives me 5, -3. And so just with that information, I know my maximal directional derivative at -1, 1 is the magnitude of that vector. Square root of 5 squared plus -3 squared is √34. And I also know at this point, -1, 1, what direction would give me that steepest possible slope? It would be in the direction of that vector, 5, -3, right? Vectors give directions, don't they? You go over 5, down -3. That's a certain direction, okay? Now there's another important property about the gradient vector as well. And this involves level curves. So I'm going to go back to our mountain that we were looking at on a previous video with partial derivatives. It's f of x y equals 9 minus x squared minus y squared. And that's an upside down paraboloid. On the earlier video, we were looking at this particular point 1, 2, 4. And I drew in some other level curves just so you can see they're all circles, right? And now let's look at a top view of this mountain. If you were up on the z-axis looking downward, you would see a bunch of these circles, right? Concentric circles representing your level curves. So if we're at this point 1, 2, now remember the summit of the mountain would be right over the origin, right? It's right along the z-axis. So you're going to, if you're looking from a top view, it's going to be right here at the origin. And so it makes sense that if you wanted to move from here and you wanted to find the maximum slope, if you wanted to, you can tell from you're right here, huh? Which direction do you think would be the steepest possible positive slope? It seems to me like you'd want to move towards the mountaintop, right? That would be the steepest slope, which looking here would be moving in this direction. And one thing you'll notice is that moving in the steepest direction is going to be moving perpendicular to the level curve, right? At all of these points right here, as you cross a level curve, you would be wanting to cross it in a perpendicular way, okay? And that is what I'm talking about. This is our property of, third property of the gradient. If you move, okay, let me refresh your memory. If you move along a level curve, your elevation is not going to change. That's the definition of a level curve, right? If I move along this circle, I'm going to get a slope of 0. I'm going to get a derivative of 0 because I'm staying at the same elevation. Okay. Now the gradient vector will point perpendicular to the level curve. And that's true because if I do my directional derivative, I will get 0 if the angle is pi over 2, right? Because cosine would equal 0 only when theta is pi over 2. So what that tells me is my derivative will be 0 if we're perpendicular, right? The gradient would be perpendicular to the direction you're moving in, right? If you move along the level curve. When the gradient and your direction of your tangent line to that curve are perpendicular. So one example on that. This one's number 33 from our book in section 9.5. We've got a function xy. We want to find the gradient at 3, 2, and use it to find the equation to the tangent line at the level curve, f of xy equals 6. That's like finding the level curve for k equals 6, right, in the notation we were using earlier, at the point 3, 2. Okay, so I'd calculate my gradient. F sub x is y and f sub y is x. Evaluated at 3, 2 gives me the vector 2, 3. Now the level curve f of xy equals 6, I would set this equal to 6. And it's easier to recognize if you solve it for y, you get y equals 6 over x. You may recognize that looks kind of like 1 over x. There's another part to it, but in the first quadrant, it would just look like this. There's a vertical asymptote and a horizontal asymptote. So at that point 3, 2, here's what we know. We know that the gradient vector would be perpendicular to this level curve, right? It would be pointing, so 2, 3, from here you go over 2, up 3, right? This vector would be perpendicular. Now, the question's asking for the equation to the tangent line, of the tangent line to our level curve there. Well, we can use the fact that the gradient is perpendicular to our level curve. So if the slope of our gradient, which is, okay, rise over run, the vector 2, 3 means go over 2, up 3, so my slope would be 3/2. So that tells me the slope of my tangent must be the opposite reciprocal, right? This must have a slope of negative 2/3. And I can use that together with this point 3, 2, and use the equation of a line with a slope of negative 2/3 to get the slope of that tangent line. Okay.